At a very high level in a system, there are two kinds of circuits we work with. One is called as the core circuits. These consist of transistor level circuits that communicate with each other within a single die. And the second are the I/O circuits, which allow you to communicate between transistors on two different dies. So I'm focusing here on the I/O signaling between transistor level circuits on two separate die, where both the package and the printed circuit board power distribution become very, very critical. At a very high level, what is illustrated on the slide is that if you have a poor power distribution network, you will stress the I/Os from a signaling standpoint. Similarly, if you have bad I/Os that you have designed, poor signaling environment will stress the power distribution network. Or in other words, one influences the other, and this is part of the reason why you need to design both of them simultaneously as much as possible. So let me start this segment by proposing a design flow. If you look at the past, in terms of how we designed a system, we always categorized our networks into two fundamental kinds of networks. One to do with signal integrity, where we looked at all of the interconnects that we then looked at as transmission lines, relied on SPICE to do a lot of the simulations. And the parameters that we were interested in here were basically the reflections as well as the rise time at the output of the drivers. Similarly, when we looked at the power distribution, we always looked at the power distribution as a standalone entity by looking at parameters like the target impedance of the power distribution network and so on and so forth. So all of the methodologies that we developed over the last 10 years always separated signal from power. Fortunately or unfortunately, ultimately you need to bring the two together, because in a system you have both parts to the system. We were able to get away with trying to look at these separately in the past because of the low communication speeds. As we look forward, where we are trying to get from the gigabit to the terabit era, you no longer can separate the two, and therefore you need a flow that allows you to combine both signal and power to look at one while at the same time looking at the other. And that is what is illustrated over here using a rectangle with dashed lines. If you now amplify that, which is shown on the right side of the slide, you will see what I'm trying to get at over here. When you look at signal and power together, one of the effects we are looking at is the signal to power coupling. And what we are looking at in terms of looking at the interaction between the two is the noise that you're generating on the power distribution network as you communicate between a driver and a receiver circuit. So therefore, that noise has a direct effect on the signaling waveform that you actually generate. And we try to do this using some kind of tool, okay, to be able to estimate the signal integrity of the waveforms while at the same time looking at the power aspects as well. And that is what is shown as both SPICE and channel analysis over here. Once that is done, you're trying to look at the timing, what we call as the I mask, to make sure that you're able to communicate at the speed that you're interested in. But this alone is not enough, because realize that the complexity of these networks is going to increase quite a bit. So moving forward, you need a design flow where you're able to iterate in this loop by going back and forth, where you have to debug, redesign, debug, redesign, and so on and so forth. So you need this optimization loop. And if you translate these into the tools, you need very high-speed tools that are able to account for both signal and power integrity effects together, and they are fast enough so that you can come up with this iterative design flow. And as I go through this video seminar, you will see a lot more of this, because that is really the focus of this seminar.